Hey Learning Hub fans, ever wondered how your phone magically predicts what you're going to type next? Or how AI can generate entire paragraphs that make sense? It's not magic, it's math. Welcome back to Learning Hub. Today, we're diving deep into the mathematical heart of recurrent neural networks or RNNs. We'll be building on the theoretical understanding we covered in the last video. Buckle up because we're about to get mathematically recurrent. Get it? Recurrent. Well, never mind. Before we dive in, here's a quick question. What do you call an RNN that's always complaining? A recurrent complainer. Okay, now let's break down the maths behind RNN. To understand the equations, we'll cover these key concepts. Input representation, meaning how we feed data into the network. Hidden state dynamics, meaning the core of RNN's memory. Output generation, how the network produces results. Loss function, measuring the network's errors. And backpropagation through time or BPTT, the algorithm for training. Alright, we'll start with input representation. Imagine you're feeding the RNN a sentence or one word at a time. Computers don't understand words, they understand numbers. So we need to turn those words into numerical vectors. The most common ways to do this are one-hot encoding and word embeddings. One-hot encoding is simple. If you have a vocabulary of say 10,000 words, each words get a vector of length 10,000 with all zeros except for a 1 at the index corresponding to that word. Word embeddings like word2vec or globe are a bit more sophisticated. They represent words as dense vectors, where each element captures some semantic meaning. Words that are semantically similar will have similar vectors. Okay, we'll denote the input at time step t as xt. This xt is our numerical representation of the word at that time step. Simple enough, right? Now, we move on to the heart of RNNs or hidden state dynamics. This is where the magic and the memory happens. The hidden state, denoted by ht, acts as the network's memory. It summarizes the information from all previous time steps. The current time step ht is calculated based on the previous hidden state ht-1 and the current input xt. Mathematically, this is usually represented by an activation function, often tanh or ReLU, applied to a weighted sum of the previous hidden state and current input. Okay, we'll break this down. WH is the weight matrix for the hidden state. WX is the weight matrix for the input. B is the bias term. And activation is a nonlinear activation function like tanh or ReLU. Tanh squashes the value between -1 and 1, while ReLU sets negative values to 0. These weight matrices are learned during training. The bias term helps the network learn even when the inputs are 0. And the activation function introduces nonlinearity, allowing the network to learn complex patterns. Now, we'll talk about output generation. The RNN need to produce an output at each time step. The output, denoted by yt, is typically calculated based on the current in the state. So yt equals to activation, weight times ht plus c, where weight is the, or wi is the weight matrix for the output, c is the bias term, and activation is an activation function which could be softmax for classification problem or a linear function for regression problem. For example, in a language modeling task, yt could be the probability distribution over the entire vocabulary, representing the network's prediction for the next word in the sequence. Time for the loss function now. How do we know if our RNN is any good? We need a way to measure its error. This is where the loss function comes in. The loss function quantifies the difference between the predicted output yt and the actual target. We'll tell that actual t. A common loss function for classification problem is cross entropy loss, while for regression problem we use mean square error. The goal of training is to minimize this particular loss function. For the entire sequence, the total loss is often the average or sum of the losses at each time step. Finally, we have backpropagation through time. This is the algorithm we use to train the RNN by updating the weights and biases to minimize the loss function. BPTT or backpropagation through time is essentially the same as regular backpropagation but applied to the unrolled version of RNN. We calculate the gradients of the loss function with respect to each weight and bias and then update those parameters using an optimization algorithm like gradient descent. The tricky part about BPTT or backpropagation through time is that the gradients can either explode, meaning become very large, or vanish, meaning become very small as they propagate backward through time, essentially in long sequences. This is known as the vanishing gradient problem and the exploding gradient problem. To combat these issues, techniques like gradient clipping, meaning limiting the size of the gradients, and using more sophisticated RNN architectures like LSTM and GRUs are used. We'll save the LSTMs and GRUs for another video. And there you have it, a mathematical overview of recurrent neural networks. It's a lot to take in, but hopefully this video has helped you understand the core concept and the equation behind these powerful networks. So, before you go, here's a challenge for you. Try implementing a simple RNN from scratch using a library like NumPy. It's a great way to solidify your understanding, and don't forget to leave your questions and comment down below. If you found this video helpful, please give it a thumbs up, subscribe to Learning Hub, and hit the notification bell so you don't miss our future deep dives into AI and machine learning. Thanks for watching, and until next time, keep learning.